有问题吗？怎样？我有 update 啊，不好下载。给我看一下，有问题吗？So we continue. It's okay. Anything okay so far? So, so we talk about the homogeneous matrix, the A. Right now we talk about the vector. We talk about matrix. We talk about vector. So any point in no matter it's 2D or 3D, okay, actually it's a vector. So the vector is have a beginning point and ending point, starting point and ending. So like this one. So this one, if a point it somewhere, so this what the starting position will be 0,0， 从原点开始。This is your ending point， 你的坐标在这里。Okay. So vector u, this is u, suppose this is u, equal to unit vector times amplitude. Any point, any sample, the data has many samples. You collect data has many samples. The samples meaning in the space, you have 1 point in the space. And any point actually is a vector from the 0, 0, the orange, 就从0到你的位置这里，那这是一个 vector. 那 vector is consist of unit vector and amplitude. 任何一个 vector， 任何一个 sample 是从单位向量跟它大小组合而成的，这很重要哈。那 what's the unit vector? Suppose this is u, right? So u divided by the absolute, this one, this called amplitude 这个大小，大小就这个，那这个叫 norm, Norm is a distance. norm, norm, 这是一个 norm。绝对值是一个 norm， 可你看绝对值是属于 norm 的一种。那 norm 是代表什么 ？Amplitude, what's the amplitude meaning? Amplitude is distance， 是距离。距离是什么？距离是 similar, the distance is equal to the inverse of similarity， 相似度的反比。相似度的反比。So when we talk about, we just talk about when we do this one, I go back to here. Right? Here. There's a distance between 2 points. You have a point P, a point P prime. So it minus means the distance between 2 points. Okay. So back to page 84. Sorry, 83. Okay, so this distance. So any point is equal to unit vector. What's the unit vector? Unit vector is a direction, is a rotation. Unit vector is meaning is a direction 的方向，任何一点的方向跟它的旋转角度。所以 unit vector equal to the physical meaning is a direction. 你走的那个方向 is also called rotation. So that's a unit vector. So any point consists of direction and the amplitude, 就几倍的单位向量。我讲一遍 ，any point, any sample in the space equal to unit vector times amplitude. Unit vector is a direction, 方向。Amplitude is meaning how many times of a unit vector. Suppose if amplitude equal to 3, it's meaning you have a 3 unit vector. If amplitude equal to 3.5, it's meaning you have a 3.5 times of unit vector. 3.5倍的单位向量那么大，那就到这一点。你要开始要想这件事情。那 for my lecture, okay, no matter is a computer vision or deep learning, we'll talk about this one, unit vector. Okay, so and the amplitude. So for the edge detection, we'll talk about. I suppose in this class, I suppose you have background of edge detection, but in the other class, Monday class for the undergraduate student, I will teach you image processing. Image processing talk about convolution. And for the edge consists of what? Edge consists of a rotation and the magnitude. So the same as this one. 就在另外一门课，我在讨论边缘侦测的时候，就边缘侦测会讲到 convolution 嘛。那 convolution 要萃取什么？萃取出来就是旋转角度跟大小，跟这个一样。每个 edge 代表旋转角度跟大小，这个也是大小跟旋转角度，所以一样的东西。好，那我们再继续讲。So for the unit vector, the denominator term, what is this one? This term is for normalization. The denominator term of unit vector, this term is a normalization. So the Gaussian distribution, when you do the Gaussian distribution, your exponential term, right? Exponential term, the denominator term of exponential term is variance, is square of a standard deviation. 标准差平方，那个是什么 ？Normalization term. 那 normalization term, what's the normalization term meaning? Meaning everybody has the same unit. For example, okay, the ratio of the money right now, okay, Taiwan, suppose Taiwan dollars and the US dollar is suppose the 30-1. So that's meaning in Taiwan dollars, suppose you have $30, you need to divide it by 30, become US $1. So you divided the term, the ratio, the term, because you try to do normalization. So after you do the normalization, you can do comparison. Okay, so normalization term is very important. And in the deep learning, we do softmax. Why we do the softmax? Because we want to normalize all the weights. The summation of all the weights become 1. So normalization is very important. 正规化很重要，这个。好，那所以你意思说，你任何空间中任何一点，你要去想这件事情，它有包括这些资讯。那这些资讯再讲一下。那这些资讯跟 What's the relationship with the eigenvector, eigenvalue? So you learn about eigenspace. You learn about linear algebra. So any matrix is here. Any matrix can do factorization 因式分解 to UWVT。OK, any matrix, any data， 你任何资料哦 ，when you collect any kind of data, the data you can try to do singular value decomposition to represent by UWVT. U is an eigenvector called eigenspace. What's W? W is eigenvalue. What's the V? V is a rotation matrix. So if I move the V to the other side, so what's the meaning of the eigenspace? Eigenspace is meaning from the original space A. After you rotate to the other new space called V, actually A before you rotate for the SVD eigenspace, you should for each term you should minus with the mean value. 你要做那个 eigen 的时候，是不是要减掉每个值都要减掉它的平均值 ？So for the A inside A, every element you should subtract with the mean value. So that's meaning everybody has the same standard. 每个人标准一样，然后再做 rotation. So equal to, so this term equal to the new space, eigenspace, and the new eigenvalue. What's the meaning here? I say again. So why eigenspace is so important? When you do the face recognition, or if you do the GAN, the GAN, the deep learning, the face recognition, the GAN, you need to use the eigen. So what's the physical meaning of eigen? It's meaning original space, and you should, for each element, you should subtract with the mean, so you should find the mean value. And you do the rotation, V, this one, V, equal to eigenvector times eigenvalue. That's meaning this one, from this space, you already rotate, transfer to the new space. And that new space will be easy for you to separate the data, easy for you to do the classification, or easy for you to do the discrimination. 就是说，为什么 eigen 那么重要？那我们在做以前做 PCA， 那现在 GAN 比 eigen 还好。那我们要做分类动作 classification。那 eigen 作用是什么？我以这个数学式来讲 ，eigen 意思说我把原来的 space， 你记得你在做那个 PCA 之前，这个每个值都要减掉它平均值嘛 ，shift， 然后再做 V 上是 rotation， 那这个会等于这两个。那意思是说，你会转到新的 space 叫 eigenspace， 变 U 跟 W。这是我讲，这是整个，这是一个点哦。This one point. This is a set of images. That's a set of data. So this is equal to what? Equal to the entire set of data you project to the eigenspace we call U. You have a scaling we call W. Scaling is the eigenvalue. So what's the meaning of the eigenvector? Eigenvector is this one. Eigenvector here is an orthonormal matrix. What's orthonormal is meaning orthogonal， 就是它是每个轴是垂直的 orthogonal， 然后每个轴是做 normalization， 所以它是一个 univector。So eigenvector is a univector， 它互相会垂直，每个 eigen one orthogonal to the eigen two、eigen three 会互相垂直，互相垂直不会影响。第二个是什么？第二是它是一个 normalization， 它是一个单位向量。We call orthonormal here. 所以 project 到一个新的 space eigenspace is easy for you to do the discrimination. Okay, and for any axis 哪一个轴，它的那个轴的那个单位实际上就是 eigenvalue. What's eigenvalue? Eigenvalue is a standard deviation. Eigenvalue is a standard deviation of Gaussian model. So PCA is a Gaussian model. PCA space is a Gaussian model because they have a mean value here. You shift to the A. You shift to the new position. And then you have a W extract from A. 你把 A 里面东西萃取出来变成高，就是说 PCA 本身是你把原来这个 space A 用Gaussian model 来 model 这个 space 的分布，那这个Gaussian model 实际上就是 eigenspace。我要讲一遍 ，for the data you collect the data, how do you model the data? Okay, for example, we have three people. 我们3个人，three persons. Each person suppose have 5 images. Person 1 has 5 images. Person 2 has 5 images. Person 3 has 5 images. Okay, and you put all together to be A. 就变成大家放在 A matrix. Right? And you move to a new space, shift. 所以就减掉这3个的平均值嘛。然后经过 SVD 就创造一个新的 ，you create new eigenvector and the new eigenvalue, and you will find out I can be modeled by one Gaussian model. Three person can be modeled by 3 Gaussian model. So PCA is kind of the Gaussian modeling because you have mean, you have standard deviation. Your standard deviation 我们有3个人，假设有3个轴，那每个轴它都有旋转角度 eigenvector。第二个是每个轴它的那个 standard deviation 大小不一样。为什么？因为我拍的光线可能跟你拍的光线不一样，那我要 normalize。所以他把它萃取出来。什么叫因式分解？你把一些 data，so what we call factorization， 因式分解，就是说他把这个 data 经过 PCA space， 他把它拆解出来了，把我们3个可能本来在原来 space 会有混在一起，经过 PCA， 他把这3个人把它拆解出来了，变成3个高讯 model， 每个就分得很开，你就很容易就分辨谁是谁。那高讯 model 包括密码，包括 standard deviation， 3个轴有3个 standard deviation， 跟这个一样。So eigenvalue is standard deviation， 每个单位不一样，因为我们光线不一样，拍的地点不一样，这样子。好，这样可以哦。这 PCA 的物理意义很重要 ，PCA 的东西。那这个都是从 unit vector 这边从 vector 来的。最后这边我补充的，昨天晚上我想一想，在我20年我都来，每次上课都会再重新 update 一下，这个我把讲义放上去。OK， so here I want to explain what is D equal to AX. This is a homogeneous matrix. However, if you use the equation format, it will be a linear combination. So AX equal to B. The A is a homogeneous matrix. B and X, or B and X is a vector. But this is kind of a linear combination here. Eigen is a linear combination. This also linear combination. So suppose y is here equal to B. So y equal to A is unknown parameters. So this one in deep learning, so W1, W2, B is unknown parameters is A. So any homogeneous matrix is a linear combination. 这个注意一下啊，任何的那个 homogeneous matrix 本身是一个 linear combination。就我们是把这个写成 homogeneous matrix 形式嘛，它原始上是一个 linear combination。那 we try to solve the unknown parameters of a linear combination using homogeneous matrix. This is also linear combination. So sometimes here what I try to tell you is B equal to X or X equal to B is a linear combination of original equation, but when you do the coding, you need to use homogeneous matrix format to write. And this one is one format of a linear combination. This is also the other one, the same. Fx, the equation equal to this constant term, so A equal to B, this one. And this is linear combination. And what's the cosine? What's the sine? This is a signal processing. Actually, cosine is x, sine is equal to y. So this one can be like a, suppose this z, suppose this term is z. So z equal to a plus ax plus by. And cosine and sine is 90-degree difference. So it's orthogonal. 为什么 cosine 跟 sin 可以这样相加？因为它两个是90度不一样，刚好垂直嘛。所以 x 轴跟 y 轴90度不一样。那 x cosine 跟 sin 本身就是一个 orthonormal 的东西，所以讯号处理为什么你们的资工系的讯号处理比较弱了哈？跑不上去。对 ，so this term can be x, this term can be y, and this term can be z. So the same is linear combination. I just try to let you know all the linear combination, no matter it's signal processing or we do the deep learning, the same. And those format that can be x equal to b. So how can we solve the A? Here, the method is this one. We call optimization process. And so in entire lecture, I will teach you how can we solve the optimization using first one, if Ax equal to B equal to 0, we call cross-form solution. We call cross-form solution. So cross-form solution is Ax equal to 0. That's cross-form solution. And we can solve it by SVD as the eigenvector and eigenvalue. And I will explain to this one. Use a real example to explain to you. 这我之后会跟你讲，就你遇到 x equal to 0的问题，就用叫做 cross-form solution， 你可以去解它，用 cross-form solution 来解它。那 cross-form solution 是用 eigenvector、eigenvalue 来解，就是你解出 SVD 以后 ，eigenvalue equal to 0, that term corresponds to an eigenvector. That vector will be your answer. When you x equal to 0, we call cross-form solution. That one, you use SVD, and then you find the eigenvalue equal to 0. That term corresponds to the eigenvector. That eigenvector will be your answer. That's called cross-form solution. If it is Ax equal to B, there's several solutions. One is a pseudo inverse. We can solve it using pseudo inverse to solve x or solve A. 有时候是 A 不知道，有时候 X 不知道哦。Second one is the SSD. So here, sum square difference. And at the deep learning, we call mean square difference. This n is equal to the number of batch size, sorry, the batch size, number of a batch 的 image， 就是 batch 里面的多少组笔资料叫 n， 所以这是 mean square difference 这个。那最后一个是用 Lagrange 来做，这都 ax equal to b 的问题。这我们后面会就next lecture when we talk about the calibration, I will explain this one. So next lecture about camera calibration, I will explain all the optimization process to you. 我全部解决。那 before, okay, like 2 or 3 years ago, people use this equation to solve the deep learning. Right now, more people use Lagrange to solve the parameters of a deep learning. So what's the Lagrange? Is this one. This original equation square. And you have one more constraint term. Usually Lagrange is this is lambda. So try to solve this. This is a constraint term. So suppose they have 2 class. 这我昨天晚上加的啦，抱歉。this is SV support singular value decomposition. SV supportive vector machine. Okay. Why is before deep learning? Why supportive vector machine is so famous? Because it uses Lagrange to solve the problem. And right now, getting more people use the Lagrange to be the loss function of deep learning because we want to have a more constraint here. Before this year, your loss function has only this term. This term is what? This term. 就是说你在这个1年前，大部分的深度学习都用这个来做，或是 cross entropy， 没有 constraint term。最近1年，最近 recent year, people this term they plus 1 constraint term, so they use Lagrange instead of mean square difference to be the loss function. So this one actually this is square, so this kind of SSD or mean square difference. This one constraint. So they cross the constraint term, so become Lagrange. And right now, more paper in deep learning, they include this term, become Lagrange. And they solve this one, use gradient descent to solve this one. And the result is better than the current result. And so that's what I say. Right now, deep learning, what they try to do is that many good methods in machine learning. Okay, so they step by step use the good method in machine learning, move to deep learning, try to solve it. But still going. Okay, 还没结束，因为才刚开始，就 deep learning 才刚开始 ，deep learning just start, just begin. So they have a long way to go. Okay, so right now people use SVM. Okay, I should say use Lagrange to do that. But why SVM before is good because they use Lagrange to solve the discrimination problems. 这样子。OK， 你既然知道这概念就好了。The last one I will try to say is the affine transform. Affine transform 就是回到一开始这里。So I talk about the Camera model. Right now, and I talk about 3D, 2D relationship between 2D and 3D. And right now I talk about, because we talk about space, we talk about the transform. So you should know the affine and perspective transform, both. Okay. So page 90在第90页 page 90，我现在92页，因为我昨天晚上加了2页的样子，在你们这里 ，OK， talk about this one。Okay. So what's the affine transform here? So suppose original square or rectangle is here. If you only have a translation, so that's this one. We call translation transform, only translation. It's meaning there's the input here. There's input. There's output. And between input and output, you only exist the translation information. So from here, center to this center, you only have a tx, ty, because it's a suppose 2D. If 3D is tx, ty, tz. Okay, so this only translation. This identity. So this without rotation. So only translation here. Only translation from here to here. You have translated tx, x, axis, and y. So here is only translation. If you have not only translation, you have rotation here. This is like a Euler angle, right? Euler angle. So you have this rotation, and your constraint is a squared plus b squared equal to 1. So this square, cosine squared plus, usually you minus equal plus sine squared. So if this one equal to 1, that's meaning you cannot do any scaling problems. You have the same object, but you do the rotation. So this one here. So this is the rotation, and this is the translation. So become here. Okay. And why we call it rigid? Rigid is meaning 那个 solid， 就不会变形，叫 rigid 啊，不会变形的，就 rigid 的东西。那 non-rigid 是 meaning is flexible， 有 deform 叫 non-rigid。So a rigid object, non-rigid object. And if we don't have this constraint, no longer require this one. If we don't have this constraint, it's meaning you have a scaling term. 你会变形，就是有时候长变比较长，变比较宽这样子，会有变形。所以这里一个 scaling term， 但是相似，所以 it's kind of a similarity, because similarity transform. So this will include is the same rotation and translation. 会变小了嘛，灯就变小。So I organize all the affine transform. So affine transform include translation, include rotation, include scaling. But scaling can be x scale can be different from y scale， 那就会变形。这个 also there is shield. Shield is like this one. But usually we don't let it occur. We don't let it occur. 我们不让它发生，所以通常不让它shield发生，这种很少发生。所以我们通常usually we affine will include, I say again, affine transform is rigid, so we'll include translation, rotation, scaling. That's it. But we'll say it's not without a shield, 不会让切线变形。我们通常这个不要，叫 rigid motion， 叫 rigid motion， 那就 affine 东西。So affine transform total has 6 parameters， 有6个参数。affine 2D to 2D, affine has 6 parameters. But if you write the homogeneous term will become this one. So this will be 0, 0, 1. Let's call affine. Affine 的这里分母 affine transform has no, affine transform is denominator only 1, only is equal to 1. 它分母就是1，称为 affine transform， 不变形。好，那第二个是 what's the perspective transform? So this is affine transform. We call the in-plane rotation is affine. Okay. What's perspective projection is out of plane rotation is this one. Or this way. So it's deformed. So perspective transform will deform. So they have a denominator term. So this both terms are not 0. So they have denominator term. 它有分母的 term. So it's a nonlinear transform. So affine transform is a linear transform. Perspective projection is a nonlinear transform. So perspective projection include affine. Perspective projection include affine because affine is only low rotation. Affine low rotation. Perspective projection include low rotation and pitch and yaw. 3 kind of rotation. 这样子。所以 perspective projection means from 3D project to 2D. That's perspective projection transform. So if this 2D you can see from 2D to 2D. This is a from 3D project to 2D. So from 2D to 2D, this is a perspective projection transform. And it will keep the straight line. 就直线还是直线这样子。好，这边我是做一些推导。那这里另外一个注意一下哈，on page probably 98, mine is 100, probably you are 98. What I try to say is in 3D, okay, the cross product can be processed by inner product in case if you need to use it, especially when you read a paper about 3D things. Sometimes this cross product, they will write like a Jacobian. This one 就是外机可以用内机来处理哦，所以有时候会遇到这个问题啊。我们做 3D 会做很多外机，像外机可以用内机方式变 Jacobian 来处理，那这个 Jacobian 就变成这样子。所以 when you see the paper, they talk about this format. That's meaning actually it's a cross product, but they use inner product format to process it. 这是就是外机本来是 this is a vector ax ay az, this is a vector bx by bz. Do the cross product actually equal to the inner product, and the ax ay az become this format. 这样子，这要注意一下啊。这本来是这样嘛，注意一下。OK。这边 So find out the page 116. I organize this one for you. 把它帮你稍微整理一下这样子。Okay, 那你再自己看。Okay, so let's say for this one, for the camera modeling, and we talk about next lecture is camera calibration. So why we need a camera calibration? And this camera calibration. So for the, sorry. So for the camera calibration, what I try to teach you is how to do what's the optimization process. So when you learn the optimization process, it's enough for you to learn computer vision, machine learning, and deep learning in my lecture. 就是我试着用这一份讲义，虽然我们讲 camera calibration， 但是我重点是要教你那个什么叫 optimization。那这个基本上就够你用了。至少我弄到现在，我这些数学就够我用的这样子。所以最难也就是这些数学而已。OK， 所以这本最主要是教你这个。那 this one 我 based on this paper， Zhang's paper， 这是那个大陆一个很厉害学者在微软这个 paper 他写的这个 paper。Now I will based on this paper talk about for the camera calibration. Now I will explain this one in details. And this is the other paper, but actually you can just write his technical report. 你用这个 technical report 来读它。那这是另外他一样的 paper 出在 journal 这样子。好，那我这里没有给你了哈，这是那个因为时间关系，我赶快先简单讲一下。这份我没给你，这个是EM方式，EM 的方式。那这个是 Hinton 就是那三大师哈。Deep learning 有 three major person. One is Hinton, the other Decamp. The third one I forget his name, but the book has. 那有一本书我给你，那本书里面上面有那个三大师都得到图灵奖了哈。这里要跟你讲什么？这篇 paper 在讲什么？这篇 paper 不要看，不适合你看，你年纪还不大，因为太难了。你看到 paper 都是数学，可以不用看。我们不玩数学 ，There's too many mathematics, so just know. Oh, okay. There's a method use EM. 这个数学那么多，我们不玩数学。那 why this one is important? Because they tell you, this paper tell you, okay, gradient descent is not good enough. But right now we use gradient descent. For this lecture, actually I will tell you is okay, here. That's the procedure for calibration. So next week I'll teach you all the process, the optimization process. So I'll teach you the closed-form solution. I'll teach you the pseudo inverse because this calibration includes both. And finally, this is sum square difference. But when you solve this one, you need to use the EM method. So EM method is very important. But why deep learning don't use EM? They use gradient descent because gradient descent is easy. It's easy to understand and easy to approach the second degree of second gradient， 就是二次微分的东西。gradient 是一次微分， 那 EM 是用2次微分来做。那这边我会慢慢，我后面会教你，教你说怎么解这个式子。然后呢，你不是用一般的这个，也是回到 homographics。那我们要怎么解这个式子？一样，我们就要用那个 Levenberg-Marguan 的方式来解，就是2次微分的方式来解。那我讲为什么 Deep Learning 不用2次微分来解，因为很复杂，因为它参数几千万太多了，很难解。那一篇 paper 跟你讲，有方式可以解，那你不要去先等他把程式写好，你再带进去就好了。让你知道说，事实上也一样，就很多新的 Deep Learning 方式都在等那些很厉害的人把 Machine Learning 或 Computer Vision 东西慢慢搬过来用，这样子。那我们next hour we will talk about Deep Learning again. Okay, so we take a break.